Section 7.8, Improper Integrals. We're going to do two different types of improper integrals in this section. The first is of type 1. A type 1 improper integral is an integral of the form a to infinity, or of the form minus infinity to b, or of the form minus infinity to infinity. What we mean by that is we have some, let's say, graph something like this, and let's say here's a, and here's some nice little function, or maybe this is a better idea of what's going on. And we want to see the area under the curve from a all the way up to, well, forever. So if the limit of a as it goes to t, so we cut off somewhere t, and we keep moving t more and more and more towards infinity, we take the limit as we move this cutoff t, and the limit of that integral. If that limit converges, then we say that the integral exists. So in that case, the integral is called convergent. If the limit does not exist, we call the integral divergent. The other possibility for type 1, or one of the other possibilities for type 1, maybe I'll draw it like this actually. So I'll put a and b in the same place, but it doesn't matter where b is. So let's say the function continues in this direction. So in this case, we have an integral from minus infinity to b. So we put our t cutting off somewhere, we look at the area underneath, and then we keep moving t to the left towards minus infinity as we take the limit. If that limit exists, then we say that this integral exists. Then, if both of these guys exist, if from minus infinity to a and from a to infinity exists, then it looks something like this. Let's say that here's a, which is equal to b in this case, and it goes off like that, and then it goes off like that. Then we can combine the two integrals, and we can get the area underneath the curve. So in this case, this is an integral from minus infinity to infinity. It's just the two of these combined. So notice that choosing a over here wasn't all that special. You could have put a over here, and you would get the exact same integral because you would still have this part, and then you would add it to the part on the right. So it doesn't matter where you choose to stop the first integral and start the second, as long as you choose to start and stop them in the same place, provided that you're doing this integral. If even one of these fails to converge, then your entire integral fails to converge. The general idea is that the way I drew it, the integral tapers off on both sides. So this one tapers off, and this one tapers off. The area underneath basically approaches 0 at some point. Sometimes integrals, well, many times, integrals of functions do not converge because the function just doesn't really ever, get close enough to the x-axis that the area underneath approaches 0. So when that happens, we get a divergent integral and we can't get the area underneath. Let's do an example. Let's determine whether the integral of 1 over x dx from 1 to infinity is convergent or divergent. So this integral, by definition, is equal to the limit, where instead of looking at the b value of infinity, because infinity is not a number, we plug in a number t, we keep our 1, and we look at this integral, 1 over x dx. This is an integral we know how to evaluate because this is just some number, and t is just some number, so then we'll just worry about the limit afterward. So we keep our limit, we do our integral of 1 over x dx, which is ln of absolute value of x. Then we just have to evaluate it from 1 to t. Well, that's going to be the limit of ln of t, because we plug in t, and then we subtract ln of 1. So that's just the limit of ln of t. But remember, natural log just goes, forever like that. The limit as t goes to infinity of ln of t is infinity. So that means the limit doesn't exist. Since the limit does not exist, this integral is divergent. This would have had to be a finite number for us to have a convergent integral with a finite area, but it wasn't. Let's do another example. We've got x e to the x dx. So from minus infinity to 0, this is going to be equal to the limit as t goes to minus infinity now. So we keep our 0, we replace minus infinity with a t, and we look at this integral. So x e to the x, that's a product. It looks like a prime candidate for integration by parts. So we'll let u equal x, then dv is equal to e to the x dx. So that means that du is equal to dx, and v is equal to e to the x. So our integral from t to 0 of x e to the x dx becomes x e to the x u times v, evaluated from t to 0, minus the integral from t to 0 of e to the x dx, uv minus v du. So this is equal to minus t e to the t minus 1, because you just plug in t, then you plug in, plug in b, so plug in 0, and then plug in t. And when we plug in 0, the entire thing is 0, so we get minus t e to the t, and then the 1 is from plugging in 0 over here, and then we just have to plug in t, and we get minus e to the t, so that's plus e to the t. So this is our integral over here. Now we just have to take the limit. So the limit of t e to the t. Well, that's just the limit of t over e to the minus t, which is equal to the limit of 1 over minus e to the minus t using L'Hopital's rule, because this is indeterminate of the form infinity over infinity. So we take the derivative of the top and bottom, and we can now put the denominator back into the numerator. So this is the limit of minus e to the t. So e to a very big number, but then it's a very big negative number. So this becomes a very, very, very small number. So it's 0. You could think of it as 1 over e to a very big number as t goes to minus infinity. So now we have our integral of x e to the x dx that we wanted to begin with. We know that that's the limit as t goes to minus infinity of this thing over here. And then we just got that limit just for the t to the t part. The minus 1 and the plus e to the t part are easier. So we calculated this one was 0, so this limit is 0. So that's minus 0, minus 1, because the limit of minus 1 is minus 1, and the limit of e to the t as t goes to minus infinity is 0. So this integral is equal to minus 1. It's convergent. Let's do another one. Let's look at this integral from minus infinity to infinity. So we've got 1 over 1 plus x squared, and that splits. Remember, we can choose the splitting value. We can cut this thing wherever we want, so we might as well choose to split it at 0, because it'll be hopefully a little bit easier to integrate over there. And that means that our other integral has to start where we left off at 0. So taking a look at the first one, we get the integral from 0 to infinity of 1 over 1 plus x squared dx is equal to the limit of the integral from 0 to t of dx over 1 plus x squared. So that's the limit. Well, 1 over 1 plus x squared is the derivative of arctangent, so that's the limit of tan inverse from 0 to t. So that is equal to the limit of tan inverse evaluated at t minus tan inverse evaluated at 0. Remember that tan inverse looks like a rotated tangent, basically. Let's see if I can draw it. So there's asymptotes at pi over 2 and at minus pi over 2. Yeah, very rough sketch for this one. I wasn't very careful. Okay, so that means that the limit as t goes to infinity of tan inverse, because tan inverse of 0 is obviously 0, of tan inverse of t is equal to pi over 2. So it just goes on forever towards that asymptote at pi over 2. So let's look at the other integral. We have one that converges, so we can keep going. If that one had failed to converge, or if it had diverged, then we would have had to just stop, because our entire integral would have been divergent. So as we go to minus infinity, we replace that with a t, and we keep our 0 at the top now. And we look at this integral, which is again tan inverse, just with the different limits. So we go from t to 0. So that's now equal to the limit of tan inverse of 0 minus tan inverse of t. So tan inverse 0 is 0, and then tan inverse t, to go to minus infinity, is minus pi over 2. So again, this thing is pi over 2. So that means that the entire integral together, from minus infinity to infinity, of 1 over 1 plus x squared dx is equal to the sum of the two integrals, pi over 2 plus pi over 2, which is just pi. So this is pretty cool. That means that if I were to draw what this function looks like, 1 over 1 plus x squared, then it's something like roughly like that. And let's label it real quick. So then this is the area underneath the curve, and it's exactly pi as you go infinitely in both directions. Neat. In our first example, we did the integral of 1 over x from 1 to infinity, and we saw that it was divergent. So what if we did the integral of 1 over x squared? Well, that would be the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx, which is the limit of minus 1 over x evaluated from 1 to t, and that's equal to the limit of 1 and minus 1 over t, because 1 over t minus 1, and as t goes to infinity, this goes to 0. So we have 1 minus 0, so it's 1. So it looks like there is a convergent integral if we have a square in here, but a divergent integral if we have a 1 in there. So in picture form, maybe I'll do it over here. This is, say, 1 over x squared. So I'll label that. And we're starting at 1. So we're looking at this area over here. So this area is exactly 1. However, from the first example that we did, if I just look at 1 over x instead, which looks I don't know, something like this compared to 1 over x squared, it still goes to 0. If I draw this infinitely enough, it's still approaching 0. However, because it approaches 0 more slowly, we end up with an infinite area. The limit does not exist. So that's very interesting. It basically begs the question, what exponents can we put on x in the denominator, what exponents p, in order to make our integral converge? What exponents are the bad exponents? So clearly 1 was a bad one, but 2 was a good one. It got us a nice convergent integral. So we already have 1 that we did. So it saves us a little bit of work. We know that if p is equal to 1 by our first example, then the integral of 1 over x to the p is 1 over x. So that diverges. So let's consider the cases when p is not equal to 1. So that means that we're looking at the integral from 1 to infinity of 1 over x to the p, and p is not equal to 1, so this is the limit of the integral from 1 to t of x to the minus p equal to the limit of x to the minus p plus 1 over minus p plus 1 by the reverse power rule. We just have to remember to evaluate from x equals 1 to x equals t. So then this is equal to the limit of 1 over 1 minus p. But p is not equal to 1, right? That's how we were able to get away with this. We don't have to worry about our denominator being 0. And we have inside 1 over t to the p minus 1 minus 1. So let's consider a couple cases in order to try to evaluate this limit. Let's think about if p is bigger than 1. Well, if p is bigger than 1, then our exponent p minus 1 is positive. So if the exponent is positive, that implies that as t goes to infinity, t to the p minus 1 is t to some positive number. It's getting super, super big. So this thing's going to infinity. So that means that 1 over that, 1 over t to the p minus 1, is going to 0. So that means that this thing's going to 0. So our integral from 1 to infinity of 1 over x to the p dx is equal to 1 over p minus 1. Because this is gone, and what we have left with is a minus 1 times 1 minus p, 1 over 1 minus p, which just flips the 1 minus p into p minus 1. So this is if p is bigger than 1. So that means that it converges when p is bigger than 1. You have to be a little bit careful. Notice there is no equal sign over here because, as we said before, it does not converge for p exactly equal to 1. It only converges for numbers p bigger than 1. Let's take a look at the case where p is less than 1. Our last possibility. So that means that our exponent p minus 1 is negative in that case. So that implies that as t goes to infinity, we have 1 over t to the p minus 1 going to 0. Sorry, 1 over t to the p minus 1 is not going to 0 in this case. This is negative. I have to flip this first. This becomes t to the 1 minus p. Because p minus 1 is a negative exponent, I want to put it in the top. So I put it in the top by making that negative exponent positive, which means I change the order. Notice p is smaller than 1, so 1 minus p is positive. So that means that t to a positive number, this would be super, super big, just like this went to infinity. Now t to the 1 minus p goes to infinity. Okay, but that was 1 over t to the p minus 1, that was this thing. So that means this thing doesn't go to 0 anymore, it goes to infinity now. So this thing diverges for p less than 1. So to answer our question, this integral converges assuming that p is strictly greater than 1. So 1 over x squared, 1 over x cubed, 1 over x to the 4th, all those nice values, that'll make this thing converge. Let's do improper integrals of type 2 now. Notice these improper integrals do not have infinity in the limits. They're just regular a and b limits. But remember that asymptotes aren't just horizontal. Horizontal asymptotes happen as x approaches minus infinity or infinity. But vertical asymptotes can happen at any x value. If you take a limit at an x value and you get infinity, then you get a vertical asymptote. So you could still have kind of a messy looking integral there. So in this case, we're looking at a discontinuity at b. So that means that our function looks like maybe something like this, where it's, you know, all nice and normal for a while, and then it just blows up at b. Maybe I'll make b happen a little earlier though. And similarly, we could have a case where it happens at a. So its function's all nice at b, and then it blows up at the a value that we're trying to integrate. So if the limit, as before, converges, so in this case we're going towards b from the left. If that limit converges, then the integral converges. If we can go to a from the right for the second case, and then that limit converges, then this integral converges. But let's say it has a discontinuity at c in between. So let's say it looks something like It's all nice, and then it blows up. So there's an asymptote, and it blows up all the way around over there. So here's A, here's B, and here's C. You would think, wow, it's insane for us to be able to get the area underneath this curve. But sometimes, if it gets close enough, fast enough, then this thing will converge, and you will be able to get the area underneath. So this discontinuity at C won't even matter, assuming that this integral converges, this one, and the other integral converges, this one. So it's similar to the definition from before, but you have to be very, very careful here, because you're not going to have infinity in your limits. So these integrals are much less obviously improper. They're still just as improper as before, but they're like incognito. So we'll have to look for vertical asymptotes very carefully. For example, over here, notice there's danger in the denominator. If we divide by 0, so we can't have x equals 2. Notice that the limit as x approaches 2 from the right of 1 over the square root of x minus 2 is equal to infinity. So there is a vertical asymptote at x equals 2, so this integral is improper, even though it might not look like it. So we've got dx over square root of x minus 2 equal to the limit as t approaches 2 from the right of the integral from t to 5. Since we can't plug in 2, we plug in t instead, and we move it closer and closer. So this is going to be equal to the limit of 2 times square root of x minus 2. When you just do a quick mental u substitution, 1 over rad u is just, when you integrate, 2 rad u, because the half cancels. So then we evaluate this from t to 5, and this becomes the limit of t to, as the t approaches 2 from the right, of 2 rad 3 minus the square root of t minus 2, which is 2 rad 3, because this goes to 0 at this point. So that's wonderful. That means that this thing converges. So we can actually take a look at the area underneath this curve. So let's say here's 1, 2, 3, 4, and 5. We have a nice vertical asymptote at x equals 2. And then here's our curve. And even though the way I drew it, it doesn't look like it's going all the way down fast enough, it apparently is. We go from 2 to 5. Our y is equal to 1 over the square root of x minus 2, and that means that our area underneath this curve is exactly 2 radical 3. Let's determine whether the integral of secant converges or diverges from 0 to pi over 2. Notice that this integral is improper because the limit as x approaches pi over 2 from the left of secant is equal to infinity. 1 over, remember secant's 1 over cosine, so that's undefined at pi over 2. We approach from the bottom, which is from the left. So that means that our integral from 0 to pi over 2 of secant of x dx is improper. So we rewrite that as the limit as t approaches pi over 2 from the left of the integral from 0 to t of secant x dx. So that's the limit of, I don't like how that pi came out. It's hard doing it that small. I should have made it bigger. You should make it bigger. So remember, we integrated secant previously. We saw that it's equal to the natural log of the absolute value of secant plus tangent. And we evaluate that from 0 to t. So that's equal to the limit of the natural log of secant t plus tangent t minus the natural log of, well, secant 0 plus tangent 0 is just 1, so this is the natural log of 1. The natural log of 1 is 0. The natural log of secant plus tangent, as t goes to pi over 2, well, that's going towards infinity. You can remember tangent looking like, as you go towards pi over 2, it just blows up. Similarly for secant. We already did that one. So this entire limit is non-existent. It equals infinity. So that means that our integral definitely diverges. Not as much fun as the previous example. Okay, another one where we have a potential issue with our denominator. All these denominators always messing everything up. So it looks like x equals 1 is a vertical asymptote, which you can verify by looking at the limit. So that means that the integral from 0 to 3 of dx over x minus 1 is equal to the integral from 0 to 1 of dx over x minus 1 plus the integral from 1 to 3 of dx over x minus 1. Because in this case, that bad number wasn't one of the limits of integration. Very sneaky, but it was between 0 and 3, so we have to rewrite our integral as these two integrals where the bad number is one of the limits of integration. This was our third case of type 2 integrals. So let's take a look at the first one and see if that one converges. So let's look at the integral from 0 to 1 of dx over x minus 1. Well, that's equal to the integral. Since we're going this way, we'll approach it from the left. So t approaches 1 from the left. The integral from 0 to t of dx over x minus 1. And that's the limit of the natural log of x minus 1, absolute value, evaluated from 0 to t. So that's equal to the limit of the natural log of the absolute value of t minus 1 minus the natural log of the absolute value of minus 1. So we get the limit of the natural log of 1 minus t, because it's the natural log of 1, and that's 0, and then natural log of absolute value of t minus 1 is the same as the natural log of the absolute value of 1 minus t if we approach 1 from the left. So this is equal to minus infinity, because approaching 1 from the left, that's like the same thing as looking at natural log as it goes down like this, approaching 0 from over there, so that's minus infinity. So that means that this integral diverges. All it took was one integral to break it. We didn't even have to look at the second integral. Once we saw that the first one diverged, we're done. This whole thing now diverges. Notice that if we had been naive, we could have written that this integral from 0 to 3 of dx over x minus 1 is just equal to the natural log of the absolute value of x minus 1 evaluated from 0 to 3. And just willy-nilly, you know, anti-derived it right off the bat. Plugged in 3, got ln of 2 minus ln of 1. ln of 1 is 0, so we just get ln of 2. But in fact, this integral does not exist. It does not converge. It is definitely not equal to ln of 2. So all of this is totally wrong. You have to be very careful with these integrals. Now, whenever you see integrals with a and b limits, you have to be very suspicious and think that there could be a discontinuity hiding somewhere in there. Always check for discontinuities. Your integral could be improper in disguise. Okay, notice natural log has a nice discontinuity at 0. Approaches minus infinity as we approach 0 from the right. So this thing definitely has a vertical asymptote over there at minus infinity, at 0. So that means that our integral from 0 to 1 of ln x dx is improper. So we rewrite that as the limit as t goes to 0 from the right of the integral from t to 1 of ln x dx. So as we've integrated natural log before, we use uv substitution, integration by parts. So u is equal to ln x, dv is equal to dx. That means that du is equal to dx over x, and v is equal to x. So we get that this integral from t to 1 of ln x dx is equal to uv x ln x minus the integral of v du, so the integral from t to 1 of dx. So that's equal to 1 times ln 1 minus t ln t minus 1 minus t. Because we have to evaluate this from t to 1, which I forgot to write. So that's where you get 1 ln 1 minus t ln t. Okay, so then we simplify that a little bit. We get minus t ln t, because ln 1 is 0, minus 1 plus t. So our limit as t approaches 0 from the right of t ln t is equal to our limit of ln t over 1 over t. Because now we can use L'Hopital's rule. We basically manufacture a quotient here. So taking the derivative of the top, we get 1 over t. And then taking the derivative of our denominator, we get minus 1 over t squared. So that's nice because that cancels and leaves us with minus t. So that limit is just 0, because now we can plug in 0. Wonderful. So that means that our improper integral actually converged. So the integral from 0 to 1 of ln x dx is equal to the limit as t approaches 0 from the right of minus t ln t minus 1 plus t. We just got this limit, so we just have to work out the rest of it, which is super easy. We saw that this limit was 0, so it's minus 0, and then minus 1, because that's the limit of minus 1, plus 0, so that's minus 1. So that's pretty cool. That means that if we look at the graph of the natural log, so here's graph of the natural log, here's 1. It's y equals ln x. This area over here is exactly equal to 1. Neat. Oh, I forgot my x. Okay, let's do a comparison theorem. Suppose that f and g are continuous functions where f is bigger than g. They're both positive, so they're both greater than or equal to 0. And this is true for some interval of x values. Then, if the integral for f is convergent, the integral for g is convergent. So what that means is we've got like some function f, right? We're saying that the area underneath f is finite. So this area that I drew the arrow to is finite. That means that if I draw another function g underneath it, right, that should definitely have finite area, right? Because it's being sandwiched by f. So that should make sense. Similarly, if I draw these functions, well, actually I could probably just use the same functions. Yeah, I'll just use the same functions. If I draw these functions and this integral on the bottom doesn't have finite area, let's say it blows up, and the other one is on top of that one, it's even bigger, then of course the one on top would have to diverge also. So your situation depends on which one's bigger than the other and whether one of them converges or diverges. Notice if the top one diverges, it doesn't give you any information about the bottom one, because the bottom one could still converge, just like for our example of 1 over x and 1 over x squared. Similarly, if the bottom one converges, it doesn't give you any information about the top one, because the top one could still also converge, or it could just blow up itself. So you have to be a little bit careful here. Let's show that this integral e to the minus x squared dx is convergent. Remember that we can't express this integral in terms of elementary functions, but it would be nice to know that it exists. So let's look at the integral from 0 to infinity of e to the minus x squared dx. So we have the integral from 0 to 1 of e to the minus x squared dx plus the integral from 1 to infinity of e to the minus x squared dx. And you might be asking, well, why would you split it up like that? There's no obvious reason to chop this thing off at 1. However, this integral from 0 to 1 is just a regular integral, so that there's no discontinuity at 1. So we know that this one converges. And it turns out that if we split it off at 1, then we can just look for x values that are greater than or equal to 1, which will give us another function that we can compare this thing to. So if we just have x values greater than or equal to 1, then that means that x squared is greater than or equal to x if we multiply both sides by x. So if we multiply by a negative, we get negative x squared is less than or equal to negative x. We're trying to make this look like e to the minus x squared. So we raise both sides to e. We get e to the minus x squared must be less than or equal to e to the minus x. And now we have a candidate for comparison. We can say that the integral from 1 to infinity of e to the minus x dx, which is still improper, but that's the limit as t goes to infinity of the integral from 1 to t of e to the minus x dx, which is something that we can actually evaluate, because this integral is just the antiderivative of e to the minus x. So we just get e to the minus 1 minus e to the minus t. All it does is give us a minus, which switches the order. So that's just e to the minus 1, because as t goes to infinity, this goes to 0. So we were able to do this integral. We cannot do this integral, but because this integral is always bigger than this integral is always smaller than the other one. So in this case, here's f, this guy. We just showed that it converges. So this area is finite. That means that this area must also be finite, this one. So we can say that the comparison theorem implies that the integral from 1 to infinity of e to the minus x squared dx is convergent because it's smaller than a convergent integral that we just found, or the function that we're integrating. The integrand is smaller. So that means that the integral from 0 to infinity must also be convergent, because the only thing missing is this convergent integral that we took off. We already know that's finite. Some finite number plus some finite number is a finite number. So this thing is also convergent. Let's do one more example. Okay, if we look at our integrand, 1 plus e to the minus x over x, as we go from 1 to infinity, that's definitely going to be greater than 1 over x, because this is 1 over x, and then we add a positive number to it. Notice the negative exponent doesn't make this number negative. This is still positive. So this thing is definitely bigger than this thing. But wait, we did the integral from 1 to infinity of 1 over x dx. We said that that was divergent in our first example that we did. So we have our integral is even bigger than one that we already know is divergent. So it definitely must be divergent too. So the integral from 1 to infinity of 1 plus e to the minus x over x dx is divergent.